So, good morning. How's everybody doing? I'm a morning person, so by the end of this talk, you will be too, because I won't give you any choice. Today we're going to be talking about fun and friendly computer science. I love live tweeters. My handle's on every slide. Take pictures. I don't care. Get that content out there. I love it. So because I only have 30 minutes, normally this talk is a full hour. I had to cut an entire section about data structures. So we're going to be doing 7 topics in 30 minutes, and this is about how fast I'm going to talk the whole time to make sure you all get your money's worth. So we're mainly going to be focusing on fundamental and introductory object-oriented programming topics because, like I said, I have 30 minutes, so there is no way I could do anything more. But if this is interesting to you, I encourage you, I'll put up the slides and you can go dig in. There's tons of stuff online. This talk is beginner and introductory focused, so if you're worried right now that you're going to be lost, you won't be. If you have familiarity with loops, arrays, and classes, you will have no problem following along the whole time. My name is Mercedes Bernard. My pronouns are she and her, and I'm a senior software engineer / engineering manager with a digital consultancy here in Chicago called Tandem. I also started a group called Dev Together, so if you've ever seen me in the Chicago Tech Slack posting about it, that's me. Why aren't you clicking? Great. So why did I put this talk together? My background is in traditional computer science. I have a bachelor's degree in it. I've been coding for about 10 years, and the longer I do it, the more I realize I don't use most of what I learned. You really don't need it to be successful in this job. But if you came into software from a non-traditional career path, whether that's your self-taught, a boot camp, you probably didn't have the opportunity to learn these things, but you'll still be interviewed like you did. And even though I know a lot of us in this room are doing front-end development where object-oriented concepts really aren't that important, that doesn't mean the interviewer knows that, and we all know that tech interviewing is kind of broken, so you may still be asked these questions even though that's not important to your job. So my goal with this talk is to show you that these topics that are used in interviewing and a lot of times are used for gatekeeping really aren't that intimidating, and they're not all that important because you probably already know it and you just don't have the words to explain it, and you really don't use this stuff very often. So my goal is you're going to walk away with this talk with a high-level understanding of a bunch of different topics. You're going to have some metaphors that you can take away to use to explain them in interviews, and you're going to have code samples that you can refer to later if you find this interesting and want to dig a little bit deeper. And if you're sitting here and you're like, Mercedes, I already know all of this, I'm going to be bored for another 28 minutes, don't worry, I guarantee you will find something useful in here to explain it to the early career devs that you're working with to teach them something or in your mentorship. If you're somebody who likes to follow along while the person's talking, you like to have visual aids, all the slides, the abbreviated version and the full version are up on my website right now, so you can go ahead, go there. It's like the second link under Chicago JSCAMP. Yeah. And then this is where you can find all the code samples. So if you do want to go dig into this later, all of the code is up there. It's got a working UI. It's got a full test suite. You can really dig in and have some fun with that. And all of the code that you're going to see is in JavaScript because we are at a JavaScript conference. But also, I want to show that object-oriented thinking is really not tied to a language or a framework. It's just a way to approach your code. If you used a functional language, you would really have to contort it to get it to do this. But if you're doing Python, Ruby, .NET, Java, Swift, like all these things, it really doesn't matter what tool you're using. Okay, so this is what we're going to be getting through today. Like I said, we're going to go quick, but don't worry, I promise you'll be able to follow along. So we're going to start with some concepts, and we're going to start with big O notation. Do we have anybody here who is like real great in the kitchen? I'm not. Yes, awesome. So if you are really good in the kitchen, you've probably heard of cooking with ratios. So cooking with ratios is where you don't memorize the recipe. Instead, you memorize a ratio of ingredients. So the amount of ingredients that you need changes in proportion to how much of the food that you want to make. Now, like I said, I'm not good in the kitchen, so don't follow any of the recipes I'm going to quote today or that you're going to see. But as an example, cupcakes follow a 4-3-2-1 ratio, where it's like 4 eggs, 3 cups of flour, 2 cups of sugar, and I think a cup of milk or something like that. And so all of the basics in the kitchen can kind of follow that, whether you're doing bread, vinaigrettes, any of that. So big O notation, why is that related? Big O notation measures the relative complexity of a function or an algorithm. Most often, you're measuring running time in an interview. If they're asking you about it, they're asking about it in the concept of running time. But you can also use big O notation to measure memory consumption, stack depth, and all the other computing resources that you can think of. We're going to focus on running time since that is the most common interview scenario, but it really can be used for a lot. So with big O notation, the actual input size to your function is unimportant because what we want to measure is the proportional complexity of the logic. See where I'm going? Proportion of ingredients, proportional complexity, yeah? Great. So this measurement is language, hardware, time agnostic because everything is relative to the input size to your function. And when we're talking about big O, we're talking about the worst case scenario. So sometimes when you're sorting a collection or you're searching for an item, you get super lucky, right? And they give it to you almost in alphabetical order, or the thing you're looking for is right at the top of the collection and it's like the second thing you look at. That's not what we're talking about. So like in a worst case scenario, if your collection is completely unsorted, what is the relative complexity of this algorithm? So let's talk examples, okay? The very first O that we're going to talk about, and O is just functional notation, but computer scientists have to make everything more complicated. So if you are a math person, this is the same as like f of x equals 1. It's just O of 1. On a graph, it's just a straight line. And so this is constant time. So what this is saying is that no matter how much of an input, how many things you're putting into your function, it's always going to take the same amount of time to run. So in this case, we are beating, what are we beating here? Combining butter and sugar. So we're going to combine butter and sugar for 3 minutes to make our cupcakes, regardless of if it's 2 cups of butter, 1 cup of sugar, or 4 cups of butter, 2 cups of sugar. We're always going to beat it for 3 minutes. It's a constant running time. That's O of 1. The next O is O of n. So this is, your linear, linear increase there. So the running time is proportional to the input size, and the running time increases in direct proportion to your input size. Is that all making sense to everyone? Okay. So in this case, we're adding eggs. So for each egg we add, we need to beat our cupcake mixture for 1 minute. So you add an egg, beat for a minute. Add an egg, beat for a minute. Add it. You see where I'm going? So for each egg we add, we're adding a minute of running time. So this is the linear complexity, O of n. If you're in an interview and somebody says, what is the O of this function? If there is a for loop, you're looking at O of n. 1 for loop, O of n. 90% of the time, you're going to get that answer right. But let's talk about O of n squared, the next O. So we're getting a little bit worse performance every time we go. So this is the running time increases proportionally with the square of the input size. And when I learned this, I was like, when do you ever do anything with the square of the input size? Nested for loops, nested iterations. So you'll see here, again, don't follow my recipes. This is going to make some really crappy cupcakes. But if I wanted to add the flour really, really slowly and mix it really thoroughly, I might use a nested for loop to break that into a very slow function. And so you'll see here I have 1 for loop, and then I have another one. That's O of n squared. If I added a third to make the performance even slower, it's O of n cubed. A fourth, O of n to the 4th. You guys got it right. Awesome. Good morning. So anytime you're looking at nested iterations, you are looking at O of n to the however many they are if you are in an interview situation. Again, 90% of the time if they're not trying to trick you and doing something really weird. Again, we're getting a little bit more contrived with my examples every time, but the next O is exponential growth. So this is O of 2 to the n. So this is if you wrote a very, very poor performing function. So if I wanted to have a Fibonacci themed party and frost all the cupcakes with a Fibonacci number, and I calculated that recursively, that would be an exponential growth. So it increases very, very quickly and gets worse and worse for very small increases in the input size. And now, because I didn't want to torture you all, and because I've really struggled to come up with an example for this last one, the last O that you'll commonly see in interviews is O of log n. This is, in my head, I think of it as the opposite of this. It's not really, but it might help to think of it that way. So O of log n, if I'm a graph, looks like this. So it increases a lot at first, and then it flattens out. And so what O of log n, a common algorithm that you'll see is a binary sort or a binary search, because you are cutting the input size in half every time, and so you can only cut in half so long, and you're approaching that constant time. That one is probably less common, honestly. If you get through these first, 4 or 5, you should be good in an interview. So when do we use it? Honestly, I've never used Big O. Not professionally. I've really only ever used it in an interview scenario. It can be helpful if you are trying to compare the performance of 2 possible implementations. It can be helpful if you work at a place like Google or a place where there are a lot of very, very passionate CS people to have a shared language. But the most helpful thing is just having an awareness of those mile markers, nested loops, thinking about how many recursive calls that you're making so that you know when you can improve the performance of your function. And honestly, I do not care if you walk away and do not remember which O is which, but just knowing that 4 nested loops is probably not great. Great, we got through the first one. Next up, we're going to set theory. So if you know Venn diagrams, you probably already know set theory. This is the example that we're going to be using for all of my set theory slides. They are very adorable Instagram accounts. I won't be offended. Pull out your phone, go follow them. They're super cute. Okay, so the first thing in set theory is the union. I do not know mathematical notation, but if you do, it's X, that little U thing, Y. So if I wanted the union of these Instagram accounts, where I've got accounts with cute dogs on the left, accounts with cute cats on the right, and accounts with both cute cats and cute dogs in the middle, I would basically be asking for all of the cute accounts. I want my Instagram feed to be so happy when I wake up in the morning. Just give me all of it. But what if I only want the intersection? So that would be only the stuff in the middle. Mathematically, it's the upside down U, I don't know. And it's accounts featuring only cute dogs and cute cats. So let's say that I really want to curate my feed. I only want most bang for my buck. I might ask for the intersection there. If I'm a dog lover, I am. I'm sorry, cat folks, but I love dogs. Not a huge fan of cats. I might ask for the difference. So that's X minus Y. That's going to get me the stuff that's only in the left circle and doesn't exist at all in the right circle. But for everybody I just offended by saying I don't like cats, you would want the relative complement, which is this Y slash X. I don't know why computer scientists do this. It's just Y minus X. It's just the opposite. And so this will get you cute cats. So no dogs in your feed, you'll only have cute cats. And then the opposite of the intersection is the symmetric difference. It's also called the disjunctive union. Again, mathematicians and computer scientists love to make really hard vocabulary, but it's accounts featuring either cute dogs or cute cats, but we're not going to do any cross-species friendship because it's just too overwhelmingly cute and I can't handle it that early in the morning. So when do we use set theory? It's the foundation of all relational databases. So if you've used a relational database, if you've written SQL, you are using set theory and you actually already know it. And then if you are a web developer, set theory is really common when we're talking about website filters. So if I'm buying a pair of shoes and I'm saying I want a size 6 or 6.5, that's a union. If I'm saying I want 6 or 6.5, but under $50, that's an intersection. So website filters, it's all set theory. All right, next up is recursion. And by the way, I make all my own icons, and I am really proud of these girls. Thank you, thank you. All right, so Russian nesting dolls are a great metaphor for recursion because each doll is exactly the same except for the size. So if you don't know what Russian nesting dolls are, well, how do you pronounce Matryoshkas? What he said is you get a doll, you open it up, there's another doll inside, you open it up, there's another doll, and you keep going until you get to the smallest doll. It's usually a solid block of wood, it doesn't open, there's no children, and then you go and you close them all up in reverse order. So recursion is the process in which a function calls itself directly or indirectly, and the function that's doing this is called a recursive function. So if you're in an interview and they say, which one is the recursive function, they're not trying to catch you, it's just the one that calls itself. And everything that you do recursively can be done iteratively, it's just fancy looping. So I know it can be really intimidating when you're getting started, but it doesn't have to be. When you're writing a recursive function, we don't want it to continue calling itself infinitely. We need to find a finite use case where it exits the loop. And so that case where it does return a finite value is called a base case, and that's usually the easiest place to start if you need to write a recursive function. The smallest doll in the Russian nesting dolls is that base case, right? It doesn't open. It's the base case, and then you go back and start closing everything up. So let's look at an example. We have two functions on the screen. One is count and one is count nested dolls. Count nested dolls is the recursive function. That's the one that's calling itself. Well, I can't. It's not working. It's right there, near the bottom of the screen. And unless you're doing something really weird with private variables or instance variables, recursive functions will always take a parameter. So in here, what we're doing is if I hand you a set of Russian nesting dolls and I tell you, count how many dolls you have, what you're going to do is you're going to open the first one and see, well, there is a child, so you're going into the else, and you're going to open the next one, and remember when you come back that you're adding 1 for this biggest doll. So then you're going to open the next one, there's a child, so you're going to go into the else. Remember when you come back, you're adding 1. Keep going until you get to the smallest child. It does not open, there are no children, and so you hit that if, that base case, and you return 1. Then you come up out of that invocation and you go to close the next one. You remember, oh, hey, I've got to add this +1. So now I've got 2. I come up out of that invocation. I'm going to close the next one. I'm adding 3, 4, 5, however many you have, and then you can return to me and say, I had 5 Russian nesting dolls. So when do you use recursion? Like I said, it's just fancy looping. So if it's intimidating, anything that you can do this way, you can do just with a flat iteration. But sometimes recursion lends itself really well to nested structures. So think mega menus on websites, breadcrumbs, file structures, things like that. Okay, we're through all the concepts. How is everyone doing? Good? Great. Okay, I've got 10 more minutes, so we're going to get through the next ones real quick. If you're ever asked the holy grail of interview questions, which is, what are the principles of object-oriented programming? They are encapsulation, abstraction, inheritance, and polymorphism. If you're like me, until I put this talk together, I never remembered which was which or how to explain any of them. So when you're done here, you'll at least know what the difference is. So the first one is encapsulation. So let's pretend that we're all writing a video game or some kind of game where the user has to move a horse across the screen. Now, do we have any horse people here? Awesome. So none of you are going to know if I got this wrong, but horses have 4 gaits. They can walk, trot, canter, or gallop. A walk is a 4-beat pace, a trot is a 2-beat pace, a canter is a 3-beat pace, and a gallop is a 4-beat pace. Now, if your user wants to play your game and move your horse across the field, and you say, hey, make it canter, do you want them to have to know that it's a 3-beat gait and which 2 feet move at the same time and what order they move in? No, that sounds pretty awful, right? No. So what you would do is you would define a method called canter that will take care of moving the horse's feet in the right order, at the right time, at the right pace. Those methods that you're making encapsulate the state of each leg while it's moving. Okay? So encapsulation is when you hide an object's state from other objects. You create a public interface, just means a method or a function, for other objects to interact with your object and mutate its state. So you're never letting another object directly mutate your object's state. That's encapsulation. So let's look at a code example. So this is what canter looks like. So you'll see they move their first leg, then they move 2 legs, and then they move the last leg. And they repeat that over and over and over again. Like I said, we've all decided we do not want our user to have to know what this looks like and like pick up each leg and move them, because that is not a fun game. So instead, what your user would do is they would use the canter method that you defined to tell it, I want it to canter for this many steps or this much distance or whatever, whatever the method is that you define. So that's encapsulation. That's all it is you don't let anybody else mutate your object's state. You give them a defined way to do that. So next up is abstraction. So everybody here has Netflix, has a TV, has used a TV. When you push a button on a remote control, something happens, right? The volume goes up, the channel changes, but there are very few finite things you can do with your remote control. And you don't need to know how it works in order to make that change happen. For example, you do not need to know that when you push the button, it gets encoded into binary. The binary is encoded into infrared light. The infrared light is sent to your TV. The TV then reverses that and converts it back into binary, sends it to the microprocessor, and then the microprocessor does something with it to get that little bar to move up 1 notch on your screen, right? You don't need to know that to know I push a button and my volume goes up. So this is an abstraction. You push a button, a thing happens, you only have a few buttons to choose from. Abstraction is an extension of encapsulation, so it's very easy to confuse the two. Abstraction refers to hiding all the internal implementation details of a class and providing very few clear mechanisms for other objects in the code to interact with it. If you've ever heard somebody say, we created the wrong abstraction, or I want a different abstraction, you can think of a TV back in the 50s or the 80s where you had to get up, turn a knob, sit back down, and go, I still can't hear it. Get up, turn the knob, and sit back down, right? Like, we got lazy and said, I'd rather push a button from my couch. The same thing is happening, it's just a different abstraction. Does that make sense to everyone? I love all the head nods. Thank you. Good morning. All right. So as an example, this might be what how you would model it programmatically. You'll see you turn it on, turn it up, turn it up, turn it down. That's the abstraction. That's all your system needs to know about. But what's really happening is, like I said before, you click the button, then it's encoded into binary, and then the binary is converted to infrared light. The infrared light's sent to the TV, and then the TV reverses the process and does something with it on the other end. You don't see any of that. You just see this. It's nice, easy to understand. That's abstraction. We are going to end on time. All right, so inheritance is the third principle of object-oriented programming. All garden plants need sun, soil, and water to survive. I'm very bad at gardening, but I do know this. If you want to learn how to garden, you're going to be at Home Depot or wherever you're buying your garden center, wherever, and you're reading those little tags in all of them, right, that tell you how to take care of the plant, how much sun it needs, everything it needs to stay healthy and thrive. If you were going to code an app that displayed each plant's care instructions, we could use inheritance to share the code that accesses each plant's needs and prints them out in a human understandable format. So inheritance supports reusability in programming. A child class, also known as a subclass, because again, computer scientists, we love lots of vocabulary. A child class can inherit all of the fields, methods, and properties from another class. This class is called the base class, or the superclass, or the parent class. So any of those, it's the class that the child is inheriting all the logic from. The child can then also choose to implement its own logic that differs or just adds to what the parent has. So for example, up here we see the class for plant. It returns whether or not the plant needs sun, whether or not it needs shade, what the string for what the planting instructions are, the string for what the care instructions are, and then we have a function at the end called learn how to garden that we would use this if we wanted to print it on that little card. It just prints it all out and formats it for us. So this would be what the geranium class looks like. And you'll see on the very first line, geranium extends plant. Extends is that keyword that tells it it's inheriting everything from plant. And this is the entire class. This is not abbreviated to make it fit on a slide. So you'll see all it does is define its properties, whether it needs sun, whether it needs shade, or water, or soil, whatever, all of that. But that extends property means it has all of the stuff on the previous slide just implicitly. So then if I had a bunch of different plants and I wanted to print all of their care instructions out, that's all I have to do. So even though geranium did not have learn how to garden defined in the class, it still has access to that through that extends keyword. Assume that begonia and coleus also were implemented the same way, and you can see they inherit it, and that would work. Last one, polymorphism. Do we have any crafters in here? People who knit? No? Okay, well, I do. So this one's for me. So if you're an avid crafter, you might know multiple crafts that you can use to create a fabric. And depending on the type or style of fabric that you want, you would use a different craft. So knit, crochet, weaving, whatever. But at the end of the day, you're doing the same thing. You are creating fabric, right? So if we were to model that programmatically, we would take advantage of polymorphism. So polymorphism is where you can use multiple classes in exactly the same way so that their concrete class does not matter. What you saw on the previous slide, inheritance, is one method to achieve polymorphism, but there are other ways to do it, including duck typing. Duck typing, if you don't know, is where you define the same method signature on multiple classes, and then you just use it and assume it's defined, and it gets its name from if it walks like a duck and talks like a duck, it is a duck. So if it has this method and it takes this parameter, it is whatever that thing is. Or if you're using statically typed languages, you might use interfaces, which it's just a language construct that defines what the contract for that class needs to be, what are the methods, what are the parameters, and then forces you to implement that. So there's like 3 main ways to implement polymorphism. We are going to use duck typing so that you all can see an example of that. So here we have a class. This is, which one is this? This is knitting. So if I wanted to create a knit fabric, this top method is my polymorphic method. This is create fabric. I just tell it how many rows of this fabric I want to create. And then the stitch row for knitting, I knit a row, purl a row, knit a row, purl a row. But all my code, or like all the consuming code is going to care about is that I'm creating a fabric. If instead I wanted to weave my fabric, maybe I want to make a blanket or a wall hanging instead, you'll see again, create fabric. How many rows do I want to create? But I'm going to weave the row, which means like 1 row, I'm going to weave the weft over the warp, then under, then over, then under. But in the next one, I'm going to go under, over, over. But at the end of the day, I'm creating a fabric. And then the last fabric you might want is crochet. So again, if this is my personal favorite, but if you're making a baby blanket or something, it's the easiest. Still, create a fabric, tell it how many rows, but all you do is you just crochet. It's really simple. You can't mess it up. But if we make an app and we let the person say, like, what is their favorite craft, you'll see I come in here. If they chose knitting, I assign the knitting class to yarn craft. If they chose crochet, I assign that. Or if I chose weaving, I assign that to yarn craft. But the last two lines are the most interesting, where I say the chosen craft equals whatever I set it to up above, and then just create a fabric with that chosen craft. So you'll see I don't care if they chose knitting, I don't care if they chose crochet, it doesn't matter to me, we're making a fabric. That is literally all polymorphism is, but it is one of the most intimidating terms in computer science. And we got through all of them in 30 minutes. Yeah. So if you liked this, you can find any of my other talks there. If you want to dig into the data structures piece of this talk that I had to cut, those are also linked here. Again, you can find my code there. And thanks.